controller part of controller part of control system. Okay, so let me just share my screen to you. Yeah, is my screen visible to you?
Yes, sir.
Yes. Okay. Okay. If it is visible, let's start with the contents. Let's start with the content. So, first of all, I'll consider that you know the basics of control systems since this is a gate-oriented class. Okay. So, I'll touch directly the concepts in compensators and controllers. Okay. So, first of all, let's start with what is meant by compensator. Okay. So what we want here is what is meant by compensator. So compensator, yeah. So compensator, yeah. So this is what we are discussing initially. So what is meant by compensator? Yes, anyone, those who know what is compensators, let's make it interactive. So you should also be talking to me. Yes, anybody? So basically, compensator is a device or it is a network which is to be added in control system, which is to be added in a control system for making it more stable or achieving some characteristics those were not initially present in the our control system, or we can say in our system, closed feedback system. So let's see an example. Let's say we have this plus minus, okay, and then we have our normal G of S, which is a system gain, open system gain. This is my C of S, okay, and this is my H of S. So what we have is we have this closed loop system, right? Let's say this is my R of S. So this is my closed loop system. So let's say this system is not providing me a desired output, but I want to use the system with some other network that will give us the required output, right? So for example, we will add here an another block called as compensator. Compensator. Now, what happens when we add this block as a compensator in this network? What it gives? The compensator will help us to obtain the desired performance from the system, right? We use compensating networks, and compensating networks are applied to the system in the form of feed forward path gain adjustments. Okay, so this is to be remembered. Compensator are used in the form of feed forward path gain adjustment. So the statement itself said it is used to adjust feed forward path gain, right? So whenever we want to adjust the path gain, we should be relying on this compensators, right? Second, second, what can be the another case? For example, a system. For example, this system is unstable. For example, the system is unstable. So to make the system stable, what we have to do? We have to adjust. We have to adjust its. We have to adjust its zeros. Sorry, you have to adjust its poles and zeros. Right? Let's take it combined. Actually, the stability of system can only be defined using poles and not zeros. But as a compensator, we have to think about both these things, poles and zeros. So to make the system stable, we can use this compensator. So unstable system, unstable system can be converted into a stable system using this compensators. What can be another necessity? What can be another way to add this particular compensator? Why we need this compensator? There can be a multiple reasons. Next reason is to, why is not working? Yeah. The next reason is to, yeah, anybody? What is the standard response of a open loop, a closed loop control system? It goes like this and then like this, right? We'll see this diagram again. Okay, so this is called as, sorry, let me clear this. Okay, yeah, let me clear this. Yeah. So the diagram is like this. Let me redraw it. It goes like this and kind of this one, right? This is my. So if you observe the first peak, this first peak, we call this as peak overshoot. Right? Now, if this peak overshoot is too high, our system will not be able to recover from this peak overshoot. Okay? In that case, we have to make this peak overshoot a little bit lower. We have to adjust this peak overshoot, right? In this case, also we can use compensators. Okay. Again, the compensating network increases the steady state accuracy of the system. Now, what is steady state accuracy? Steady state accuracy is this. What is the steady state error between the system output? This is my system output, and this is desired output. So the difference between these two is steady state error, right? So what this compensator do? Compensator increases the accuracy of the system or accuracy of the steady state system. That means it reduces the steady state error. Again, what can be done using compensators? The compensating networks also introduces poles and zeros in the system, right? So this compensating networks also add poles and zeros into the network. So what happens when we add poles and zeros? Anybody? What can we do by adding poles and zeros? We can make the system's response change. We can change the system's response, right? So we can make the system more stable. We can make the steady state error. We can reduce the steady state error. We can reduce the peak overshoot. We can reduce the response time. We can increase the response time. All the changes can be done by adding poles and zeros into the transfer function of a system. So it is very much important, or it is a very much important topic of compensation as far as system behavior is concerned, right? So in real life situations as well, the compensators are very much used. Okay, now we'll see how we add these compensating networks to our control system. Okay, and based on that there are different names given to this addition of compensators. Let's say, for example, as we have seen, let's say this is my, let's say this is my R of plus minus. Then we have compensator. Then we have G of S. Then I have this output C of S. Okay. Then I'll be having this H of S here. I should make it at a rectangular block, which is G of S. Then this is my feedback. Okay. This is my R of S. Can anybody tell me why we always give negative feedback? Yeah, anybody? Why we give always negative feedback? There is a question. Why we give negative feedback?
It reduces the overall gain.
It reduces the overall gain. Yes. What does it mean by reducing overall gains? Okay. Okay, let's give me the examples, two examples. One example where we give positive feedback and one example where we give negative feedback. Question is, this type of questions come, right?
Sir, when we use negative, sir, when we use negative feedback, it reduces noise, distortion,
Yeah.
and sensitivity to external changes.
Okay. So what can be the examples? Okay. Okay. And when we give positive feedback,
For the
let's focus
larger
on
output
concept.
voltage,
Okay. 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 Let's focus on concepts today, guys. Questions can be handled like from the books or anywhere, but let's focus on concepts first. Okay. So when we give negative feedback, what happens? Because of negative feedback, overall gain reduces. That is very much right. But when we take feedback from the output, the fluctuations in the output can also be given to the input, which can be reduces, which can be subtracted rather from the input at this instant. Let's say this is from t minus 1 and this is at t. So from input at point t, we can subtract the fluctuations. Let's write like f at t minus 1. So this increases the stability of a system. So by using feedback, we increases the stability. We increases stability, right? Again, when stability increases, it gives steady state response. It gives us a steady state response. Okay. But what happens when we give positive feedback, guys? Or I'll better give you an example where this positive feedback is used. Do you know oscillators?
yes,
In oscillators, we give positive feedback. Right? Why we want oscillator to have positive feedback? Because we want this oscillations to be continued. Right? If you give negative feedback, what happens? The response will be like this. Right? Are you getting? If you give positive feedback, the response would be like this. And if you give negative feedback, what happen will your output will eventually be faded down and you won't get oscillations anymore. But this red line, what you see, is very much important, very much important as far as amplifiers are concerned. Why? What we want in amplifiers, that the oscillation or the noise in the output should be reduced. So negative feedbacks are mostly used in amplifiers and other networks, whereas the positive feedback is mostly using oscillators. Got it? Yeah. So let's
Yes,
jump
sir.
back to our original. Yeah, let's jump back to our original discussion. Okay. And let's focus on the type of networks we get based on the position of a compensator, right? So when we connect compensator in between this point, the input and the system gain, that is G of S, open loop system gain, then this kind of compensating network, or this kind of network or a system network, is called as series compensation. It's called as series compensator. It's called as series compensator. So what happens in series compensator? The compensating network is connected in the forward part in between the input and the open loop system gain, that is G of S. Right? What if we connect this in the feedback loop? What if we connect this in the feedback loop? Then the network will look like this. This is my R of S. Okay. This is positive, negative. Okay. This comes, this again positive, negative. This again comes here. This is my G of S. This is my compensator. Okay. And this is my H of S. This is my feedback. Okay. Now feedback goes here again. So if you observe this diagram, there is a difference between these two networks, the previous one and this one. Now here your compensator is connected in a feedback loop, right? So this is called as feedback compensator. Right? So the question may be like, you may have given the 3-4 diagrams, and based on that, they will ask you to differentiate between the different type of compensators. So this is feedback type of compensator because the compensator is connected between between the output and the input, right? So this is compensating the output signals coming into an input, which are the feedback signals. These are the feedback signals. So along with that, this compensator is compensating the feedback networks, using feedback network as an input for this compensator, and the output of compensator is provided to the input at this G of S. So if you see, this kind of arrangement is called as feedback compensators. Okay. There is another type of compensator in which the compensator is connected in the feedback loop, but along with that we have yeah along with that we have a dedicated feedback channel, or we can say the feedback from input to output and output to input as well. So let's draw that. We have plus minus like this. We again have this one plus minus, and then we again have plus minus. Okay, let's draw it in fast. So this is my G of S. This is G of S. This is the output, right? This is my compensating network, which is given like this. So if you see, this is connected directly without any feedback gain, right? With the unity gain, you can say. And then we have here a compensator, and then it is connected right here. Then we have a separate feedback. Then we have a separate feedback gain, a feedback loop. You say it connected from here. Okay. Now, in this case, if you observe this feedback, now the name. Let me write the name. This is called as load compensator. It's called as load compensator. Yes. Okay. Now, why it is load compensator? If you observe, this compensating signal is going as an input to this input line, which is this one input network. Along with that, this output is also provided here. So what we are doing is we are not just compensating the feedback line, we are also compensating the output, or we are compensating the signal which is going actually to the load connected to this network, and that's why it's called as load compensator. Okay. Now we have seen three different types of compensators, or the arrangement in which the compensators are connected. This is the first arrangement, load compensator. Then we have feedback compensator, and then we have series compensators. We have three different type of compensators connections. But what actually inside of, okay, what actually we have, what is there inside, what is the inside structure, or what is the structure of compensator? What is the structure of compensator? What does compensator have? Right, that is the important question. Right, so compensators are mainly, or the compensating networks mainly of two types. Right, compensating network is lead compensator and second is lag compensator. Now, what is meant by lead and what is meant by lag? Okay, so let's see. In lead compensator, the complete name of this is phase lead phase lead compensator, and this is obviously phase lag compensator. Now the phase is a term, lead and lag are the two different terms. Now what is meant by lead, that we will see. What is meant by lead? If some point is here, let's say this is the point 1, and something, or the point with, and the point, let's say 2, is in front, or it is ahead of the point 1, then we say the point 2 is leading. Point 2 is leading. So in this context, if you say phase lead, that means if by adding this network, which one, this phase lead network, phase lead compensating network into the system, if by adding phase lead compensating network into the system, its phase should lead. Right? That means when we add this phase lead compensator network into a transfer function of a system, the phase of the transfer function system or the complete system should be in leading side. So if we consider this as the initial phase, and this as the phase after adding the phase lead network, then physically observing the phase of this point is leading than the phase of this point, right? So this is the advantage of this phase lead compensator. Right, now let's go in detail. If you understood what is meant by phase and lead and lag, let's go in detail, and let's find out what is meant by phase lead compensator and phase lag compensators. Okay. So let's write phase phase lead compensator. Now, a system which has one pole and one dominating zero. Now, it is a system. It is a system with one pole and one dominating. I'm writing this because I want to discuss this point. One dominating zero. One dominating zero. Okay. Now tell me, what is meant by dominating zero? Okay, you first tell me, are we compatible with the terminologies pole and zeros? Everyone? Let's say this is my transfer function T of S, okay? And this is my A0 suppose, then A0 or A1 minus S, or let's say A2 minus S, and so on, upon B0, B1 minus S, B2 minus S, and so on. Okay, if this is the transfer function, then if I equate the denominator, if I equate the denominator equal to 0, if I equate denominator equal to 0, then I'll get the values of S as B1, S is equal to B2, and so on. So these values are called as, poles of the system. Whereas if I equate the numerator equal to 0, then I'll get the values of S, as as uh, A1, A2, and so on. So these values are called as poles of the system, sorry, zeros of the system. Right? So from numerator we get zeros, and from the denominator we get poles. So what we are saying is the phase lead compensator is a system with one pole and one zero. One pole and one zero. So it is having one factor on the numerator and one factor on the denominator. Right? This is my transfer function. So if you tell me what is meant by this term, which is called as dominating zero. Anybody? What is meant by dominating zero? Okay. For example, we have, a system whose the system, for example, this is for example, this is my system. It is the axis called J omega, right? And for example, I have a one pole and one zero, same as that of phase lag, phase lead, and phase lag compensators. For example, okay. So let's take an example of phase lead, as we are taking phase lead, and let's consider we have one pole and one zero, right? If the zero, listen this carefully, if the zero is marked by round and pole is marked by cross. So if the zero is present near to the origin as compared to the pole, if the zero is present near to the origin as compared to pole, then it is called as dominating zero. Okay? And if we have a pole near to the origin with respect to the zero, this is called as dominating pole. Okay. So once the terminologies are clear, we were at we were at phase lead network, and what we are discussing is a system. A phase lead compensator is having one pole and one dominating zero, right? So this network is called as lead network. Okay. So the basic requirement of phase lead network is that all poles and zeros of transfer function of the network must lie on negative real axis, right? So if we have this axis, then everything must lie on negative side of the axis, right? So where should the poles and zeros lie? Poles and zeros lie should be on this side, that is the negative side. This is the very important condition, or you can say constant in having phase lead compensation network. That's a basic requirement, right? So if we draw the circuit for phase lead compensation network, it will be like RC filters. For example, let's draw the network. Let's draw the network. This is my capacitor here. This is my resistor here, and then this is my another resistance here. This is my E0. This is my R2. Or let me draw the fresh diagram. This is not looking nice. Okay. So this is my capacitor. This is resistance. This is another resistance. It's my R2. This is my R1. This is my capacitor. The current flowing through this branch, let's assume as I1. I1. Let's assume the current flowing through this is I2. This current flowing through this is I. Okay. This is my input. Let's say input voltage is E1. Let the output voltage is E2, or E out would be better. And the current which is coming in this side, that is I1 plus I2, is same as that of I1. So this is again I. So I is flowing through this R2. Let's mark as I. Okay, and this current will go back to the input. So that is nothing but again I. Okay, is the circuit diagram clear to you? So this is my lead or phase lead compensation network. Okay. Now this phase lead compensation network, if we solve, we'll get its transfer function, and then we'll be plotting its pole and zeros on the diagram to see how it will affect our network. Okay. So this is my phase lead compensation network. Let's solve it one by one. Let's solve it stepwise. Okay. So what we do is, for this network, let's apply a laws to get the value of I1 as. If you want to find out I1, what do you get? Yes, current passing through this capacitor. What is the current passing through capacitor? It is C d by dt. Yes, anybody? EI minus E0, right? And what do you get by I2? Basically, we'll applying KCL at this point, that is I is equal to I1 plus I2. So we want to find out I1 and I2 first. What is my I2? EI minus, EI means input, EI minus E0 upon R1, right? So total current, that is I is equal to I1 plus I2, right? So this I will be C d by dt ei minus e0 plus ei minus e0 upon r1. If you solve this, what do we get is, yes, anybody? What we get is E0 upon R2 equal to this expression, right? Because what is I? I is the current which is passing through this resistor. So E0, which is the output voltage, E0 divided by R2 is nothing but this current. This is the potential between the points is E0 divided by R2 is this current, and this is the actual current which is flowing through this network as well. So this is I, and this is also I. So this current is equal to the current flowing through R2. So R2 current flowing through R2, this I is given by E0 by R2, which is given by this one, and the current which is this can be calculated in this way. So these two are same. So it is C d by dt, right? Ei minus E0 plus Ei minus E0 upon R1. If you solve this, what do we get? If we solve this, what do we get? We have to solve this by using Laplace because we want to find out the transfer function. So let's find out by applying a Laplace transform. What do we get is 1 by R2 into E0 of S, which is the Laplace transform of E0, that is output voltage, is equal to 1 by R1 in bracket E of I of S minus E0 of S, bracket complete. Then we have plus CS in bracket EI of S minus E0 of S, right? If we neglect the initial conditions, what do we get? This we have written neglecting the initial conditions. Let's write here neglecting initial conditions. Okay, so what do we get finally? We get 1 by R2 into E0 of S is equal to, plus 1 by R1 E0 of S plus CS E0 of S is equal to EI of S upon R1 plus CS into EI of S. So ultimately, the transfer function is nothing but output upon input. So E0 of S upon EI of S is my transfer function that I can get by 1 plus S CR1 upon R1 divided by R1 plus R2 plus S into R1 R2C upon R1 into R2. If you solve this, you'll get a simpler expression, that is R2 upon R1 plus R2 in bracket 1 plus SCR1 divided by 1 plus, I'm not able to write here, 1 plus SR1 R2 C upon I'm not able to write here, guys. Okay, so I'll rewrite this step in the next slide. So what I get is what I get is the transfer function, that is T of S is equal to E0 of S upon EI of S is equal to R2 upon R1 plus R2 into bracket 1 plus CSR1 upon 1 plus SR1 R2 into C divided by R1 plus R2. Can be again simplified considering the values of constants. For example, let alpha is equal to R1 plus R2 divided by R2 and tau as R1 into R2 upon R1 plus R2. So my simplified transfer function will be E0 of S upon EI of S is equal to 1 upon alpha in bracket 1 plus alpha S tau divided by 1 plus S tau. So this is my transfer function. This is my transfer function. This is the transfer function for phase lead compensator. Now from this transfer function, what we get is, oh sorry, yeah. So from this transfer function, what we get is we'll get the pole and zeros. So that's we are interested in, to finding the poles and zeros for this transfer function. So if you observe from this transfer function, what we get is we get a pole at a location of -1 by tau, and we'll get a zero. We'll get a zero at this point, and we'll get pole at -1 upon alpha tau. If we plot this, on a plot, it's a S plane. This is J omega. This is the real axis, which is sigma. Okay, this is my origin 0. Okay, this is my pole. Let me draw it by another color. It's a different color. Let me choose red. This is my pole. Okay, it is given by -1 by tau. Okay? And we have a pole here. Whose value is -1 upon alpha tau. Now, if you observe clearly, this zero is closer to the origin. And that's why it's called as dominating zero. And this is away from that of the origin. Right? If the situation is reversed, then we call dominating pole. Okay, this is just for now. So you can say the lead compensator, zero is more dominating than pole, right? Now as this zero is more dominating than pole, what happens in these situations? Yes, if zero is more dominating than the pole, what happens? This situation adds a positive, this is very important, guys. This adds a positive phase angle to the positive phase angle to the system, angle to the system when connected, in series. This adds a positive phase angle to the system when connected in series. What does it mean? It means that let's say in simple example, when we had it like this, this is my compensator, this is my G of S, this is my output, and from here we took feedback, that is H of S, right? And what I said while explaining this is, when we add compensator, our network or the complete system should be leading, right? Now, why this is leading? Because the pole is dominating. This adds a positive phase angle. Let's say this is my phase. And if I'm in positive phase angle, so it will go in this direction. Now this is called as leading side and this is called as lagging side. So addition of positive phase angle will make this system to lead, right? So whenever we have this compensator in series with the system, then it adds a positive phase angle, and it makes the whole system as leading in phase. Is it okay? Now what is the phase? By how much phase it will be leading? That we have to calculate. How can we do this? Okay, let's move towards next slide. Let me tell you how we do it. So the way we do it is by calculating the phase angle. Now how to calculate the phase angle? If you remember the transfer function, let me write it again. If you remember the transfer function, which is E0 of S upon EI of S is equal to 1 upon alpha in bracket 1 plus alpha s tau upon 1 plus s tau. Now this is my transfer function. If we replace s is equal to j omega, if we replace s by j omega, we can find out the phase angle, right? Now I'll write it directly. Okay, well, I'll write it directly. I won't go and solve this. I'll write it directly. That is theta of omega is equal to tan inverse of omega tau minus tan inverse of alpha omega tau. Okay. Now when we substitute s is equal to j omega and we'll take alpha as less than 1, then the resultant value of phase is given as tan inverse of omega tau and minus tan inverse of alpha omega tau. Now this is the phase given, but what is the maximum phase? By which a system can lead, right? That can be represented by phi m. And what is the value of this maximum angle? Now we know when we have any expression and we want to find out the maximum value of that expression, what we do? We'll take its derivative and then equate it to 0. The same we are going to do in this case. So by doing this, what we do is we'll take the derivative of this equation 1. Let's say take derivative of equation 1 with respect to with respect to theta, and then equate it to 0. So we get alpha is equal to 1 minus sine phi m and 1 plus sine phi m, right, which represents the value of alpha in terms of theta m, which is the maximum, which is the maximum, yes, phase by which the system can lead. So 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 if we solve this, we'll get phi m is equal to, we get phi m is equal to 1 by alpha. Okay, we skipped some steps in between so as to like avoid the derivations, lengthy derivations. So we just came to the value of phi m, which is the maximum phase offered by phase lead compensator. So that is equal to 1 by alpha, and we know what is alpha. Alpha is yes. What is alpha? What is alpha, guys? Alpha is equal to R1 plus R2 upon R2. So 1 by alpha is R2 upon R1 plus R2. So phi m is this one. Now see, this is how the questions will be asked. They will give the network and they will ask the maximum, phase angle offered by this lead network. So in this way, we can find out the value of phi m directly using the values of resistors connected in the network. Okay. So the so as we have now the value of okay, this is the last slide. Let me take, yeah. So as we have the value of phi m, which is the maximum phase lead angle, and it is given by 1 by alpha, and that is equal to R2 upon R1 plus R2, right? So from the network directly we can find out the value of phi m, which is the maximum phase lead angle. Now what is the effect of, or what is the effect of this particular phase angle or phase lead compensator? Okay, what are the effects we have seen? Okay, just revise a little bit. Yeah, we have seen different type of compensator connections, right? Let me change it. We have seen different type of compensator connections. Then we have seen what is the phase lead compensator, why we need phase lead compensator. Then we have seen what does it mean by dominating pole and dominating zero, right? Then we have seen this network which is of phase lead compensator, and in this phase lead compensator we have the value of this R1 and we have the value of R2, and we have taken this derivation and we come to the conclusion that the maximum angle offered by this phase lead compensator is equal to R2 upon R1 plus R2 upon R1 plus R2, whose values are known to us through the network, right? But what happens, or what is the effect of this phase lead compensator when we connect this to our system, right? So let's write down the effects offered by, or the effects of this phase lead compensator, right? So the first effect is it increases kV. What is kV? kV is the velocity constant. if you remember, the steady state conditions, that is ESS conditions, steady state response of the system, then we have Kp, Kv, and Ka. This is you can see. I mean, you can refer this at a topic of this steady state response of the system. So in steady state response, we have this velocity constant, and our phase lead compensator network increases the value of Kv. Now, what happens when Kv increases? The slope and the magnitude plot reduces the gain crossover frequency, right? What happens when Kv increases? The slope of magnitude plot affected. When we increase the Kv, the slope of magnitude plot get reduced, right? And where it reduces? It reduces at the gain crossover frequency. Do you remember gain crossover frequency and phase crossover frequencies? Yeah. When the phase plot and gain plot we calculate, based on that plots, we'll get phase crossover frequency and gain crossover frequencies. So the slope of this magnitude plot get affected by the value of Kv, and 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 its slope reduces at the gain crossover frequency, so that what happens, the relative stability of system improves. Or in simple way, what we can say, when the slope of magnitude plot reduces at gain crossover frequency, the relative stability of the system increases. This is another takeaway point. What is the takeaway point? When the slope of magnitude plot reduces at gain crossover frequency, the relative stability of the system increases. And why this happens? This happens due to the error which is present. This happens due to the error. Where should I write? Yeah, I'll write it here only. The error is directly proportional to the slope of a magnitude plot. The error is directly proportional to the slope of magnitude plot. So when the magnitude plot or the slope of magnitude plot reduces, error will also get reduces, and reduction in error causes system to be more stable or relatively stable than the previous one, right? So this is how it works. So by adding phase lead compensators in the network, the relative stability of the system increases. The value of Kv, which is a velocity constant, also increases. Third, when we say the slope of magnitude plot decreases or reduces, it indirectly affects the phase margin, and the phase margin increases, right? So let's write phase margin increases. Phase margin increases. What we have seen next, the slope of magnitude plot reduces. Slope of magnitude plot, plot decreases. What is another point? What is another effect? Relative stability increases. Relative stability increases. Yes, what is another point? Yes. What if when phase margin increases and slope of magnitude plot decreases, what happens? The system becomes more faster. The response becomes faster. The system response becomes faster. So I'll write response, PO response becomes faster, right? So these are the points where these phase lead compensator affects, right? Have you understood, guys? Have you understood this? Yes or no?
Yes, sir.
Yeah, okay. Now these are the effects of phase lead compensator. But what are the advantages then? These are the effects. What are the advantages? Yeah, let's take one more slide. Okay. Let me just add one more slide here. Let me just add one more slide. So these were the effects, right? Now, if we know the effects, what is the advantages? That we have to see again, right? So there are few advantages. I'll just tell you what are the advantages. Let me select the pane first here. Let's change the slide. Let's take the pane. Okay. Now the advantages are due to the presence of phase lead network, the speed of the system increases. Right. Now we have just seen in this slide phase margin increases. Now phase margin means the shift in there is a shift in gain crossover frequency. If you remember the curve, the phase margin and gain crossover frequency are related. So because of this phase lead networks, there is a shift in gain crossover frequencies to a higher value. And if there is a shift in gain crossover frequency to a higher value, the speed of system increases. So system becomes more responsive. This is what our statement is, right? So let me just take a different color. Yeah. So because of this, the system becomes more responsive, or we can say the speed of system increases, and that is always required, right? The advantages of this phase lead compensator is the speed of system increases. And what is the second advantage? We have seen this curve where there is a peak overshoot, and due to this effect of or due to this phase lead compensator, this peak overshoot also reduces. This is the second most important advantage of phase lead compensator. So whenever you have been asked to tell the advantages of phase lead compensator, these two advantages are very much important, right? What are these uh, two most important advantages? First, the system becomes responsive, and the peak overshoot reduces. Now these are the advantages, but what is the disadvantage? Can anybody tell me? Because it would be exactly against the advantages. Advantages क्या है? What is the advantage? Advantage is it makes the system responsive. Now if the system is more responsive, let's take this new slide. Let's say if the system is more responsive, or I can say more sensitive, responsive, or you can say sensitive. तो क्या होगा? What will happen? If the system is more responsive or sensitive, what thing is going to get affected? Anybody? Okay, let me draw this diagram. Okay, see this very carefully. Now we have this. Oh, sorry. This is the generic curve for or the standard curve for feedback system, closed loop feedback system. Okay. Now I'm saying that by adding a phase lead compensator, the system becomes more responsive or more sensitive, right? So let's say I'm getting the steady state response. Okay, I'm getting the steady state response, but my system is more responsive. So what will happen? So since this is my steady state response, this is my steady state response. Okay, but since my system is more responsive, slight change in the input, slight change in input can change output, right? So slight change input can change output. So let's say my system is having steady state response and there is a slight change in the input, so my output also varies. But what this output is, this is steady state output. So my steady state output or steady state response is not improved. Steady state response is not improved using lead phase compensators. So my steady state response is not improved using steady state compensators, and that is the biggest disadvantage of steady state. Sorry, biggest disadvantage of phase lead compensator. Okay, yeah. Shall we take a break of 5 minutes? Then we'll start with phase lag compensator. हेलो अभी कैसे कैसे नहीं बट अभी अभी वो तो हो गया अंकल नहीं ओके 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 ठीक है हेलो हेलो
Yes, sir. Hello.
या कैन वी टेक अ ब्रेक ऑफ 2 minutes
Yes, sir, sure.
या let's take a break of 2 minutes just
Okay, sir.
then we'll start with a new topic. Yeah, just take a break of 2 minutes. Yeah. Sorry, guys. I had to give some important documents to the office. That's why I left for a minute. So, shall we start again?
Yes, sir.
Yeah. Okay. So, are you guys getting what I'm teaching to you or not? Because, yeah, not getting any responses. Are you guys getting or not? समझ में आ रहा है कि नहीं? Yeah, yeah. मुझे बताओ, if there is some doubt or anything, you can tell me, okay? Okay. So let's start with another topic, or you can say the same topic but with a second part of it. It's called as phase lag compensators. We have seen phase lead compensators. Now we'll see phase lag compensators. Okay. Now intentionally we can think of these phase lag compensators as exactly opposite of the phase lead compensators, right? But let's see in details. What we have is here phase lag compensators. Okay. Now phase lag compensator is basically a system with one zero and one dominating pole. In phase lead, we have dominating zero. Here we have dominating pole, right? So if I draw pole zero structure, then there would be a pole and there would be a zero. Now since this pole is closer to the origin, it's called as dominating pole, right? Initially we had dominating zero. So let's draw a diagram of this phase lag compensator, and let's see how we can derive an expression for the various parameters. So if we have this resistor R1 here, and then we have a resistor R2 along in series with a capacitor, then this network is called as phase lag compensator. Now this is my resistors R1, this is my current I. Okay, this is again my current I. The same current is flowing through this branch as well. This is my resistor R2, this is my capacitor C, this is my output voltage E0, this is my input voltage EI, right? So, and the same current goes back into input, that is I. So if we solve this, what we get is the input voltage. The input voltage can be written as, by using KVL, can be written as, yes, anybody? I into R1 plus I into R2 plus 1 by C integration I dt, right? Similarly, the output voltage can also be written as IR2 plus 1 by C integration I dt. Okay. If we take the Laplace transform for both the equations, what do we get? We get EI of S is equal to R1 into I1 of S plus R2 into I1 of S, or sorry, instead of I1, I2, it is I only. plus, what do we get? 1 by Cs into I of S. And for output voltage, that is E0 of S is equal to R2 into I of S plus 1 by Cs I of S. And we know the transfer function is, that is T of S is equal to output voltage divided by input voltage, that is equal to yes, R2 upon R2 plus 1 by Cs divided by R1 plus R2 plus 1 by Cs. Right? If you solve this, we'll get a transfer function which is equal to R2Cs plus 1 upon 1 plus Cs into R1 plus R2. Right? Now when we substitute, let's take tau as R2C and beta as R1 plus R2 upon R1, then we'll get a transfer function, a reduced transfer function as, and this is for lag network, right? And this is nothing but 1 plus tau S upon 1 plus beta tau S. Now this is my transfer function. Now from this transfer function, if you observe, we have a high frequency gain, equal to 1 by beta and a pole equal to minus 1 upon beta tau and a 0. Okay, and I have right here, and a 0 equal to minus 1 by tau. So let's plot this all the parameters on our pole 0 plot. So what we get is like this. This is sigma, this is j omega, this is my S plane, right? So this is my origin, this is my, let me take another color. So this is my pole, and you see my pole is located at 1 upon beta tau, and this is my 0, which is located at minus 1 by tau. Okay. So here our pole is dominating. Here our pole is dominating, and if the pole is dominating, what do we get? If the pole is dominating, then the grain crossover frequency increases. Right? We'll go into details and effects of this into more. Before that, let's find out the maximum phase angle. How do we find out the maximum phase angle? As we have done previously, let's take S is equal to j omega and beta let's find out the phase angle. For that, we'll replace S by j omega and we write the equation, so that we'll get, I'm skipping the expression, I'm writing directly the output expression we'll get. So we'll get theta of omega equal to tan inverse of omega tau minus tan inverse of beta omega tau. Now, if you observe, in both the cases, this expression is almost same, except 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 the value of beta. At earlier expression, this was alpha. Okay. Otherwise, the expressions were same. The difference is the value of tau and beta for lead, for lag is different than that of the lead one. So there, alpha and tau and alpha has different values, whereas in lead, uh, this beta and beta and tau is having different values. So you have to keep these values in mind. This expression is same for both the phase lead and phase lag network. Okay. So from this, if we take the derivative, if we take the derivative of this equation 1, and if we equate it to 0, we'll get the expression in terms of beta, and that is equal to 1 minus sine theta m upon 1 plus sine theta m, where theta m is the maximum phase, where theta m, just a minute guys, just a minute. Yeah, okay. So is it visible? Yeah. So yeah, where we are? Yes, this beta is the maximum phase lag angle. Sorry. This phi m is maximum. Uh, this phi m is maximum phase lag angle. Okay, so phi m can be calculated from this expression number 2, and it is equal to, and it is equal to, it is equal to, yes. Can anybody tell me what is the value of phi m? Guys, am I audible? Am I audible or not? Hello? Have I lost the connection? Okay, just a minute, let me check. Have I lost the connection?
No, sir, you are audible.
Okay, I'm audible. So tell me, what is the theta m? Tell me what is theta m? Come on, calculate. Last time I calculated the value of theta. Will it be same or it will change? Will it be same or change? So the expression was same in earlier case as well. So at that time this was alpha. Okay, let me just change the ink color. We have seen the same expression last time, and instead of beta there were alpha. So the value of theta m was 1 by alpha. Now since the expression is same, only this character has changed. So the value would definitely be 1 by beta.
1 upon beta.
Right?
1 by beta.
Yes, exactly. So the maximum lead, the maximum lag angle that we can get by using this network is 1 by beta, right? Now, since we have calculated the values of this maximum angle, let's see what will be the effect of this. What will be the effect of this phase lag compensation on our system. So let's say effect of phase lag compensation on our system. So what are the effects of phase lag compensation on system? Let's note it one by one. Okay. Now these are the important points. Expression you can do it yourself, but these are the important points. So what we understood out of this expressions and what we can like uh, what effect this lag compensation will be doing on our system. This is important. Now the first effect is the gain crossover frequency increases. Let me write gain crossover frequency increases. Yes. What is meant by gain crossover frequencies? Yes, anybody? Okay. From where we find out the gain crossover frequencies? This is omega GC. If you remember the plot, magnitude plot and phase plot of a particular system. Yes? Have you remembered or not? Yes, anybody? So the gain crossover frequency is the point at which open loop gain first reaches the value of 1. Remember, open loop gain when reaches to the value of 1, we take that point and we make that point as a gain crossover frequency. The frequency at which open loop gain reaches to 1, first time reaches to 1. Remember? So that is our gain crossover frequency. Now, what it says is it increases the gain crossover frequency. Now, what does it mean by increases the gain crossover frequency? Obviously, the phase margin will increase, right? Whenever phase margin will increase, then only gain crossover frequency can increase. So the second point is phase margin will increase, right? What is the next point? If both gain crossover frequency increases and gain margin will increase, it will result into decrease of bandwidth. Okay, so decreases the bandwidth of a system, right? Decreases the bandwidth. Now what will happen on the response? What will the effect on the response? Now see guys, it is very much clear that the phase lag network has the opposite effect that of the phase lead network. We have seen, and in case of response, the response of the system was become, yes, becomes very much sensitive or very much responsive, or you can say fast. So in this case, what will happen if the phase lag compensation is applied? The response of the system will be slower. Response of the system becomes slower. Anything else? What can happen again? What happens to the rise time and settling time? let's say the question is, let's say the question is, consider a control system, closed loop feedback control system, to which phase lag compensation is applied. The effect on rise time and settling time are. So option A, both become larger, or first increases, both increases. Option B is both decreases. C is settling time increases and response time decreases. And fourth option is settling time decreases and response time increases. What are the options? The question is, let's say we applied a phase lag compensation to our control system. What will happen to the settling time and rise time?
Option C.
Option C. Option C is settling time increases and response time decreases.
Yes.
Okay. Anybody else? Anybody else? Now the answer of this question is in these four options. Actually, these are the hints for this question. Anybody? Again, try to read the above points and try to answer the question. The question is, what will happen to settling time and rise time if we apply phase lag compensation?
Option B.
Option B, both decreases. B or D?
B, sir. Decreases.
D for Delhi. Yeah, this one. Okay. Settling time increases and response time increases. Okay, I'll give you one more hint. Okay, I'll draw this diagram. Based on that, you can answer.
Option A.
Okay. This is my rise time. Okay, I'm drawing it very roughly. This is my rise time. This is, let's say, this is my settling time, somewhere here. This is my settling time. Okay, are you able to see this? Now you tell me, settling time is this, rise time is this, and this is my steady state. So settling time is this one. What happens? Let's check out the first third point. Let's check out the third point. It decreases the bandwidth. Bandwidth is the difference between maximum and the minimum frequency we are having. Let's say this is maximum, this is minimum, so this is my bandwidth. Okay. Now if my settling time, if my bandwidth is getting reduced, that means the time taken by the system to rise will be more. Again, the time taken by the system to settle down will also be more. So the time window between these two will be small. So bandwidth or the response, or I can say, what I can say is the bandwidth. Okay. So if the bandwidth is lesser, then the settling time will increase and the rise time will also increase. Rise time and settling time will depend on the bandwidth of the system, or vice versa, you can say. If the response time of the system is more, then the bandwidth is less. So response of the system becomes slower. This is also a hint for this question. If this point and this point are both the hints for the system. Response time of the system becomes slower. That means it will respond slowly. So the response time is more. So it is increases. Again, since the response of the system is slower, the settling time will also increase. So both is going to increase irrespective of the other parameters. So based on this point, we can answer this question, right? So the effect of phase lag compensator is to increase both settling time and rise time of the